for today, we are actually going to look at part 2 and 3 of the calculations. All right, if we're on our lab handout, part 2 and part 3 starts on page 8 of the lab. You'll notice that number 1 says graph the temperature versus time on a separate sheet of graph paper for each of the 3 reactions and extrapolate the line back to find the instantaneous mixing temperature T mix for each reaction. Record this value in the part 2 data table. So we're going to graph just like we did yesterday. So that's why I'm going to go into Google Sheets, and what I'm actually going to do is I'm going to go through, we'll do each reaction together. Now, because we have our graph 1 on this first tab, I'm going to create a new sheet for each graph that I create. Now, yesterday I showed how you can copy and paste it into a Google Doc, but I also forgot that in Google Classroom, you can just turn in a Google Sheet as well. So if you want to just, you'll turn your lab in, and then if you want to just turn in this Google Sheet, you can. Right? It'll have all of your graphs on it. So down here in the very bottom left-hand corner, I'm going to click on Add Sheet. And what it's going to do is it's going to create a new sheet down at the bottom. And what I'm going to do is I'm going to rename each sheet based on the part that I'm working on. So to rename it, I'll click on the arrow. I'm just going to rename it first so that way I don't forget. So this will be part 2, reaction 1. Some people in other classes just named the tab graph 1, graph 2, graph 3, graph 4. However you want to label it is up to you. Now what we're going to do is we're going to go in and graph just like we did yesterday. So I'm going to do time in seconds in column A, temperature in degrees Celsius in column B. We are looking at part 2, reaction 1. We are going to fill in the data from data table 2. This is why having our data tables labeled makes it easy to reference. So for data table 2, time is still every 20 seconds up to 180 seconds. So I'm going to highlight 20, 40, 60. And I'm just going to drag down. I don't need 200. So if you show Google Sheets what you want the pattern to be like, you can then drag down. And if you drag too far, you can delete. I did delete the 200. Now temperature, I'm going to record from data table 2. So this starts with 35.9. And remember that we have the how to create a graph in Google Sheets page. It's the very, very back of the lab. But we'll go through it together. If you are creating graphs more quickly, you can definitely use the how to create a Google Sheets page. So once we have all of the data in our data table, we're going to just highlight the numeric data, just the numbers. So you can just drag to select everything, and we can go to Insert Chart, or there's another button over here that's Insert Chart, but either one works. Let it think for a second. Oh, good, it created a scatter plot. If for some reason your graph did not create a scatter plot, as soon as you create a chart, the chart editor over on the side pops up. If it doesn't say scatter chart, if it says line chart instead, you can click on the drop-down menu and make sure that scatter is what is selected. So then we're going to go through the process that we did yesterday. We want to make sure we have our title for our graph. And so to create a title, we'll go to the Customize tab in Chart Editor. And we'll click on Chart and Axis Titles. And where it says Title Text, I'm going to rename this So this is graph 2. This is the second graph that we're creating. So just like with data tables, the graph needs a number. I'll say part 2, reaction 1. I'll do temp versus time. So graph 2 is important, and it's also important that we remember to add this as part 2, reaction 1. I'm going to center it just for my own sake. You can change the color, you can bold it or italicize. I don't really care. I just want to make sure you have graph 2 and then part 2, reaction 1 in the title. So our y-axis and our x-axis are already labeled. If for some reason your axes are not labeled, you can click on where it says chart title. You can actually change horizontal is the x-axis, vertical is the y-axis. You can add a title there, but we already have our title. All right, so then we're going to add a trend line. So we're going to go down to the next menu, which is series. Click on series. And we're going to scroll down to where it says trend line. Check that box. Draws the line for us. I'm going to scroll down a little bit more because we want to see the equation of the line. Less math for us to have to do. So where it says label, we want use equation. Now, since our data does not fill up the whole graph, we can change the y-axis. So I'm going to scroll down to the vertical axis menu. Because vertical axis, I want to change the scale of my y-axis. And so to do that, we can just change our minimum and maximum values. So my minimum, we really could do 35 and 36. So I typed in 35, it automatically went to 36. You could also type in 36. Now we can actually see that the line doesn't necessarily hit every single point, which is fine. It's an experiment. But this has the data filling up the entire graph. So that's graph 2. Now, before we go on to graph 3, this y-intercept right here, this 35.9, it tells us in the lab that that is T-mix. In your lab notebook, right underneath data table 2, we have 3 variables. T-mix is that y-intercept. T-mix was 35.9 degrees Celsius. Right, so T-mix was 35.9 degrees Celsius. Now we're going to do the same thing for data table 3 and data table 4. So I'll go back into Google Sheets. I'm going to click the plus down in the bottom left-hand corner. So I'm just creating a new sheet within this one doc for every data table. So part 2, reaction 2, and then we'll just go through the process again. So let me flip to data table 3, which is part 2, reaction 2. Time. So all I'm doing right now is filling in data from data table 3. So for data table 3, every single data point is 24.3 degrees Celsius. So just to make sure that Google Sheets knows that it should be the same number, I just entered 24.3 3 times, and then just drag it down to the bottom. In data table 3, the temperature every single 20 seconds was 24.3 degrees Celsius. Now we'll go through the process again, highlight all of the numeric data, insert chart, and then again, if it's not a scatter plot, you can change the chart type, make sure it's scatter. Then we'll go into customize. Really, there's 3 things we want to do. We want to rename the the chart, rename the graph. We want to add a trend line, and we want to change the scale of the y-axis. So I'll start by going to chart and axis titles. So this is our third graph, graph 3, part 2, reaction 2. And the reason that we're creating these graphs is so that we're able to get the temperature at time 0 easily. It allows us to extrapolate the data. All right, so then for the series, scroll down, trend line. So it draws the line to connect all the points. For label, we'll choose use equation. Now, we don't really have to change the scale because it's just a straight line, but we could. So if I go to vertical axis, I'll make it between 24 and 25. Oh, I don't want the axis line. All right, but so I could do between 24 and 25. We could do between 24 and 24.5. But this at least just kind of blows up the graph a little bit. So here's our y-intercept. This is T-mix for data table 3. So underneath data table 3, in your data and observations, underneath data table 3, T-mix is 24.3 degrees Celsius. So now we have T-mix for data table 1 from yesterday, data table 2, data table 3, and now we'll create the fourth and final graph. So I'm going to add another sheet to the bottom. So now I have these 4 tabs down here along the bottom. I'm going to rename this one part 2, reaction 3. I could go back and label them graph 1, graph 2, graph 3, but if there's 4 tabs, it'll be easy to look at all of the graphs. So finally, the last set of data is coming out of data table 4. The last set of data is coming out of data table 4. Time is every 20 seconds. So for this, it only really changed a little bit. But we have our time every 20 seconds, our temperature. Then just like we did before, I'll highlight the numeric data, insert chart, and then make sure it's scatter. We'll go into chart and axis titles, and we'll rename this. So this would be graph 4. What is it? Part 2, reaction 3. So rather than making all of our graphs by hand, we're just using Google Sheets to make our graphs for us. So we have a title, has a number and a title. I'm going to go into series, the next menu. We want that trend line. The whole point of making these graphs is to find the line of best fit. So if I scroll down, label, use equation. Because once we have the line of best fit and we have the equation of the line, that y-intercept is our T-mix. And then lastly, I'll go to vertical axis. And I'm going to change the scale. So then before it looked like all of the points were pretty much on the line. When we zoom in on our graph and we make it fill up as much of the graph as possible, then we really see, okay, not as much of these lines, or not, the line doesn't fit every single data point. So now, this was our fourth graph. Here's our y-intercept. So underneath data table 4, T-mix is 35.5 degrees Celsius. So now we have T-mix for every single reaction. That's important because that gets utilized in delta T. So if we take a look at our calculations, The first calculation of part 2 was graphing. So I'm going to go ahead and go into my lab notebook, flip to where we ended off yesterday. So yesterday we did part 1. Today we're going to continue on with part 2. So I'm going to label, kind of do a subheading. Okay, part 2 says calculate the enthalpy of reaction. That's kind of our subheading within the lab handout. So I'm just going to label part 2 delta H reaction. Just like we labeled part 1 heat capacity of calorimeter, right up here at the top. When we split everything up, we labeled part 1. We're going to label part 2. So number 1 says to graph. So now that we have our graphs and data tables labeled, we can just reference it like this in our calculations. So there's calculation 1. Calculation 2. So now we're getting into the math again. Calculation 2 says calculate the amount of heat evolved in each reaction, which is Q reaction. So I'm solving for Q reaction. It's assumed that all of the heat of reaction is absorbed by the solution and calorimeter. And so what they did is they took our first law of thermodynamics equation that we've been using, Q reaction plus Q solution, and in this case plus Q cal, because we solved for the heat capacity of the calorimeter. They rearranged that. And they said Q reaction is negative Q solution plus Q cal, and started plugging in all of the numbers. They also tell us down here delta T is T mix minus T initial. And they say assume the density is 1.03, specific heat is 4.18. So remember, you only have to actually show one reaction in this section. So I'm going to label this calculation Q reaction. Then I'm going to do the calculation over to the side. I'll also just make a note that says reactions 2 and 3 in data tables. Because you only have to show one sample calculation when the rest is the same. So we're going to work through this just like we've worked through it before. So we're going to show the calculation for reaction 1. We're going to look at how to calculate this for reaction 1. So first law of thermodynamics says Q reaction plus Q solution plus Q cal equals 0. And we have to include Q cal because in part 1, we solved for C cal. So I'm solving for Q reaction. I'm going to leave that alone. Q reaction is what I'm solving for. I'm going to leave that alone. Which means I should plug in variables for everything else. And it tells us in here that Q solution is MC delta T. So mass of solution, specific heat of solution, delta T of solution. And Q cal is just C cal delta T. So I'll just plug all the values in. Now, for the mass of solution, we did not put anything onto a balance. We used volumes. If I flip back to my data and observations, we used 50 milliliters and 50 milliliters. So total, we used 100 milliliters. This is why they gave us the density. So over here off to the side, kind of like we did in our solution calorimetry problem at the beginning of the week, I'm going to solve for mass of solution off to the side. We had 100 milliliters of solution. I don't want milliliters, I want grams. I need to use the density. They tell us in number 2, the density is 1.03 grams per milliliter. 1.03 grams per 1 milliliter. 100 times 1.03, that's just going to move the decimal place over. 103 grams. There's our mass of solution. Mass of solution will be the same for every single reaction. So for reaction 1, reaction 2, and reaction 3, mass of solution is the same because we use 50 milliliters every single time. So Q reaction plus 103 grams. C solution, it tells us to use 4.18. Delta T is what's going to change for each reaction. Delta T is what's going to change. It's not going to be the same for everything. So, over here off to the side, so it's almost like I'm going to do what I did before with this little dotted line. It tells us in here that delta T of solution is T mix minus T initial. Right, T mix minus T initial. So now I have to look back. Let's see, what are we in? Reaction 1. What was our T mix for reaction 1? 35.9 was our T mix, our y-intercept. All right, and then minus T initial. So if I go back, we're going to have to average them for our initial temperature. Ideally, they're the same temperature because they've been sitting out. Lab is not ideal. So I'm going to average these two for the initial temperature. 23.2 plus 24.9 divided by 2, 24.05. That's our initial temperature. This delta T is what changes for each reaction. 35.9 minus 24.05. So there's our delta T, 11.85. C-cal, oops. C-cal is what we calculated in part 1. The heat capacity of the styrofoam cup. Heat capacity of the styrofoam cup, 40.42. That's not going to change. This is going to be C-cal for this entire lab. And then again, times delta T. So we have Q reaction. We have MC delta T of the solution and C delta T for the calorimeter. Delta T is always the same for the solution and the calorimeter because it's all the same. It's all the surroundings. So if I plug all of this in, 103 times 4.18 times 11.85 is 5101.899 joules. 40.42 times 11.85 is 478.977 joules. So if I add the two and I flip the sign, negative 5580.876 joules. So I kind of did two steps at once because I ran out of space at the bottom. So Q reaction plus Q solution plus Q cal equals 0. So I added these two numbers together and I moved it to the other side to get Q reaction. Negative 5580.876. So that's reaction 1. This number we can put underneath data table 2. So if we flip back to our data and observations, under data table 2, you should have T mix filled in. That was 35.9. Now we have Q reaction. Q reaction, again, under data table 2. This was the first reaction. Your Q reaction is what we just solved for. Go through and see if you can calculate. You don't have to show it in your calculations. If you want to, that's fine. But you don't have to show it in your calculations. Do reaction 2 and reaction 3, just like what we did here. Mass of the solution will not change. Specific heat of the solution will not change. C-cal will not change. What you're changing for reaction 2 and reaction 3 is delta T. So for delta T for reaction 2, Did you guys get something like 1.05?
Yeah.
Yeah. So your delta T for reaction 2, basically the only difference between reaction 1 and reaction 2 is that delta T is 1.05 degrees Celsius. I got Q of reaction to be negative 494.508.
Sorry, I have another question.
Yeah.
We don't have to write this in our thing at all?
No, so you only actually have to show one sample calculation. So like this counts as our sample calculation. So by saying like reactions 2 and 3 are in the data tables, once you solve for like Q reaction of reaction 2, you can just plug it right into that blank in the data and observations.
Okay.
Yep. So like, yeah, I got negative 494.508 for reaction 2. So for Q reaction under data table 3, we plug that in, and then we'll do the same thing for data table 4. All of our calculations that we're working through today are based on reaction 1, like the ones that we're actually showing. So to prevent you from like doing lots of extra writing in a lab report, you always only have to show one of the sample calculations, and then you can do everything else just in your calculator. And then just plug it into like a results table like what we have in our data and observations. So I'm ready for my next page. So I went on to the next page and just wrote calculations continued because I was at the very bottom for the last calculation. So we're on part 2. I'm going to put parentheses just to remind myself that we're on the part 2 calculations. So calculation number 3 within part 2, this is actually the last calculation in part 2. It says calculate the enthalpy change, delta H reaction, in terms of kilojoules per mole for each of the reactions. Record the value in the part 2 data tables. So delta H is what I'm now solving for. So before we solved for Q, Q is just in joules. Now I want to convert the heat just from joules to kilojoules per mole. So as we're looking at reaction 1, I am going to put in parentheses reactions 2 and 3 in data tables. So I'm just going to show reaction 1. That's all you have to show is just one sample calculation. So I already forget what we got for Q. Hold on. So for Q, we got negative 5,580.876 joules. That was our Q value. Remember that Q is an amount of joules for a specific amount. To convert to delta H, we need joules or kilojoules per mole. So I'm going to need to get moles on the bottom. So over here off to the side, I'm going to show the mole conversion. So for every reaction, we used 50 milliliters of 2.0 molar solutions. So for every single reaction, we used 50 milliliters of 2.0 molar solution, which meant that we didn't have a limiting reactant because every single reaction that we did was 1:1:1. And so it doesn't matter which reactant we pick. I'm not even going to write a substance because it's the same calculation no matter what. I'm going to solve for moles. Remember that molarity is moles over liters. So 50 milliliters is 0.05 liters. So multiply that by 2. I probably could have done that without a calculator, but it's fine. 0.10 moles. So every single time the reaction used 0.10 moles, which means this was the amount of heat released when 0.10 moles of each reactant reacted. Now, delta H is kilojoules per mole. Kilojoules. Right now I'm at joules per mole. So I'm going to add an extra conversion factor to go between joules and kilojoules. Kilo is bigger. That gets the 1. There are 1,000 joules in 1 kilojoule. So, negative 5580.876 divided by 0.1 times 1,000. So I do all of my steps at once, but notice how I use parentheses. Negative 55.8. Yeah. Negative 55.8 kilojoules per mole. There's our delta H reaction. That gets plugged in. So this is reaction 1, which is data table 2. This is delta H reaction that we'll put underneath data table 2. Lots of flipping back and forth. So this negative 55.8 goes in this delta H reaction underneath data table 2. So you should have T mix, Q reaction, and delta H reaction now filled in. We have our one sample calculation. We don't have to show this again. Here's the only difference between reaction 1, 2, and 3 is the Q that you started with. The Q is different for every reaction. You divide by 0.1 and 1,000, you're going to get your delta H. So go ahead and do reaction 2 and reaction 3. You do not have to write it in your lab notebook. The only difference is the Q that you're starting with. So for reaction 2, I had a Q reaction of negative 494.508. That's what you're going to start with up here for reaction 2. Reaction 3, I had a Q reaction of negative 5,887. That's what you're going to start with here. All right, so take just a minute. Did you guys get similar numbers for those Q reactions? Because delta T for reaction 2 was 1.05. Delta T for reaction 3 was 12.5. Delta H reaction for reaction 2 is a pretty small. So here's what I had. I just wrote them down so that I remembered. So for reaction 2, I had delta H reaction of negative 4.94508. You're keeping out all your sig figs. If we round to 3 sig figs, negative 4.95 kilojoules per mole. And then for reaction 3, I had a delta H reaction of negative 58.87 kilojoules per mole. So you just did all the part 2 calculations. Right? The whole point of this part of the lab was to actually go through and calculate the delta H reaction for each of the 3 reactions that was conducted in the lab. So the last part is actually looking at verifying Hess's law. So before we move on to part 3, any other questions on like Q, delta H, where we need to plug in numbers? So we should be done flipping. Well, no, I take that back. We're not quite done flipping back and forth. So part 3 is verifying Hess's law. So I'm going to go ahead and label kind of the subheading, part 3, Hess's law. So within part 3, number 1 says, write the Netionic equations for the 3 reactions involved in the experiment Show how the first two reactions are arranged algebraically to determine the third. So this is going to be, I'll label netionics. So we get to review netionic equations. Now, we're going to go through the netionic equations together. I'm going to do it on a different piece of paper. Then we will transfer the netionic equations into our lab notebook. So for netionic equations, this is why writing each of these reactions was important. So reaction 1 was HCl plus NaOH yields NaCl plus H2O. Reaction 2, we had NH4Cl, NaOH, NH3, NaCl, and H2O. And then ammonia and HCl makes ammonium chloride. So I'm going to start by looking at, scoot this down. Reaction 1. HCl plus NaOH yields NaCl plus H2O. Now, I didn't write my states of matter, but that's okay. So we're going to look at the netionic equation on a different piece of paper, and then we'll transfer them over into our lab notebooks after. That way we try to keep it looking as neat as possible. So remember netionic equations. We break apart strong electrolytes. Strong electrolytes are strong acids, strong bases, and soluble salts. So a soluble salt is something that is aqueous and has potassium, nitrate, ammonium, or sodium in it. Remember, the only state of matter that even has the potential of breaking is aqueous. So water isn't even going to break apart because it's a liquid. So I have to keep that together. Only aqueous solutions can break apart. So then we have to ask ourselves, all right, HCl. Well, it starts with a hydrogen, so it's an acid. Is HCl one of the 7 strong acids? You're like, wait, what? Yeah, it is. I didn't know you had to remember your strong acids and strong bases for today. Strong acid. Let's see if I can name them. HCl, HBr, HI. Those are the binary. So just 2 elements together, right? HCl, HBr, HI. We have HNO3, H2SO4, HClO3, and HClO4. Those are your 7 strong acids. So that means that strong acids break apart into their ions. NaOH. Well, you have 2 ways of telling that this will break apart. One, it has sodium in it, and it's aqueous. It has potassium, nitrate, ammonium, or sodium, and it's aqueous, it's breaking apart. Also, NaOH is a strong base. Remember that bases make a lowercase b on the periodic table with hydroxide. So we have Na plus, OH minus, NaCl, so this is aqueous and has sodium, so it's going to break apart. And then H2O is a liquid, it stays together. There's my complete ionic equation. We need net ionic. We have to cancel out spectators. What are the spectator ions in this? What's the exact same on both sides? Na plus and Cl minus. So my net ionic, H plus OH minus yields H2O. So I'll put that in my lab notebook. So net ionics. Reaction number 1. H plus OH minus yields H2O. Reaction 2. So I flip back in my lab notebook to reaction 2. This one's a little tougher because it has ammonium chloride and ammonia in it. NH4Cl plus NaOH yields NH3 plus NaCl plus H2O. All right. So NH4Cl has ammonium in it. Remember, potassium nitrate, ammonium, and sodium break apart. going to break apart into NH4 plus and Cl minus. NaOH has Na plus in it, has sodium in it. It's also a strong base. NH3, that's ammonia. Ammonia is a weak base. Weak base does not break apart. So I'm going to keep NH3 together. Even though it's aqueous, it's a weak base. NaCl breaks apart. And water stays together because it's a liquid. Okay, so if I look at this, do I have any spectators in this equation? Na plus and Cl minus. So we have NH4 plus OH minus yields NH3 plus H2O. So I will flip back to my lab notebook, equation 2. NH4 plus OH minus yields NH3 plus H2O. And then finally, reaction 3. A reaction 3, NH3 plus HCl yields NH4Cl. Now I know there's some people that can look at this and immediately see what the spectator ion is. If you can, great. If not, that's fine. So NH3 again is ammonia. Ammonia is a weak base. It does not break apart. So we have NH3. HCl, we've already said, is a strong acid. And NH4Cl is ammonium chloride. Has ammonium in it. It's going to break apart. Do we have any spectator ions here? Is there anything that can cancel out? Cl. So our net ionic equation is NH3 plus H plus yields NH4 plus. So NH3 plus H plus yields NH4 plus. So there's our net ionic equations. And then the second part of this calculation, this is still part of our calculations. The second part of this says, show how the first two reactions are arranged algebraically to determine the third. So they basically want us to say, how will Hess's law work? If I want to rearrange, if I want to manipulate equations 1 and 2 to equal equation 3, what would I have to do? So if equation 3 is my overall reaction, what do I have to do to either of these equations to add them up to get to this? Carter? Flip the second one. All right, so all we're going to say underneath is flip reaction 2. And once we flip reaction 2, we just add the reactions together. So flip reaction 2 and add reactions 1 and 2 together. So we're essentially, we set up Hess's law, and it wants to know how can we manipulate the first two equations to equal the third one. And so then calculation 2 says, calculate the value of delta H for the third reaction from the values of delta H determined for the first two. So I'm going to label this calculation delta H reaction using Hess's law. That's the label for the calculation I'm going to give it. So to use Hess's law, I'm gonna need the delta H for reaction 1, and the delta H for reaction 2. But we just calculated those. And it wants to know what is the delta H for reaction 3. So if I look back at what we just calculated, here's reaction 1. Negative 55.8 kilojoules per mole. Reaction 2, negative 4.95 kilojoules per mole. And then it wants us to actually find equation 3 using this information. So delta H reaction, equation 3. So if we have to flip reaction 2, what are we going to have to do to delta H? Make it positive. So it's going to be plus 4.95. I don't have to do anything to the first one because then everything else will cancel out. So plus negative 55.8. All I'm doing right now is showing the work for Hess's law. I'm showing us adding the two values together. That's all calculation 2 wanted. Wanted us to use Hess's law, manipulate the equations. And then finally, calculation 3 says find the percent difference between the calculated and measured values of delta H for the third reaction. So calculation 3 wants percent difference. So to calculate percent difference, it's essentially like percent error. We're going to take the, I guess we'll call this actual delta H from number 2. That's this. All right, the actual delta H from number 2 minus experimental delta H. Experimental delta H was in data table number 4, divided by the experimental delta H. All right, so both of these are from data table 4. And then we multiply by 100. So our measured delta H was measured experimentally, recorded in calculation number 4. And so for our percent difference, we will have negative 50.85 minus what we had in calculation or in data table 4, which was negative 58.87 divided by negative 58.87. Now we want to remember that we want to take the absolute value of this entire thing. Oh, I should split this up. All right, we want to take the absolute value of the entire thing. We don't want a negative percent. So negative 50.85, not bad. 13.6% difference. Based on our data from the other two equations, we had a 13.6% difference. Not a bad percent difference. And those are our calculations. For post-lab questions, so just really quick with post-lab questions, do this, so I remember this is first period. These post-lab questions, there are 5 of them. It's just like, what is calorimetry? Why did we use a graph? Like, what was the point of using a graph? So think about what we were able to solve for. What does a negative mean in an equation? So post-lab questions, there are 5 of them. And then if you actually look at the rubric for this lab, it's all data analysis. Remember, data analysis is where you summarize what happened in the lab. So in part 1, we were able to find the heat capacity of the calorimeter. It was this. Part 2, we did 3 different reactions. We were able to find the delta H, which was this, this, and this. And then talk about, based on our delta H values, we were able to use Hess's Law with only a 13.6% difference, and then just talk about some possible sources of error. Remember, with calorimetry, sources of error, we use a cardboard lid and assume that no heat escapes. Maybe not the best assumption. And you have to do it really quickly. So if you don't do calorimetry fast enough, heat's going to escape. And so we might not get the most accurate data. So, those are 2 sources of error right there. It's all about heat escaping. And then conclusion. So purpose, did you fulfill it? Why or why not? Try to be specific in terms of, like, if you say, yes, we fulfilled it, give me like a number. We calculated the heat capacity of the calorimeter to be this.